Hi, Philippe.
Bonjour. Hello.
Bonjour.
So now I have two computers with Zoom, so I don't know what which one is most reliable.
Sorry? I
May
didn't.
I try a little? I have two computers with Zoom, both with Zoom. So may I try to share screen?
Yeah. Well,
So I share screen. Okay. Now it tells me you have deactivated the sharing screen by participants. I think probably somewhere you have a way to allow sharing screen by participants.
Can you try now?
I will try again. Okay. It seems it works. So I have to decide what to share. Okay, I want to share this. Okay, can you see it?
Yep, perfect.
Okay.
I can.
So it's this kind of current speaker stuff.
Oh yeah, that's the Cabello proof, right? Yes.
Cabello speaker, yes.
Yeah. Good.
Okay, so it seems it works now. That's fine, perfect. Yeah. So anybody can do something.
Yeah, I'm gonna leave it like this. So basically, only one participant at a time can share, but that's gonna be enough. And then, depending on the discussion, you feel free to share whenever you.
Okay, and if I do that, is it better? So there are two ways to do it. Either I can do that. So can you see it full screen now?
No, but I think it's coming. No, yes, it's coming. Yeah. So it really it doesn't change much. So if you feel you prefer the other one, I think everyone can see perfectly well, even if you don't do full screen.
Mm-hmm.
As you
so the other one, there is so this way, and there is still another way which is doing that stuff, but it's more or less the same.
Yeah, it's the same, really. Like, do whatever you prefer. I think everyone.
Now there is this, you see a black thing at the bottom, no?
The black thing, you mean the to go further and back? Yes, I do.
So it's hiding some letters, no?
Yeah, it does. So actually, well, it's not a big deal. But if you go to the other version without the presentation mode.
So this is a standard mode. So you can see it also like that.
Yeah, exactly. Or this one. That's fine too. That's great.
Okay. So the big one is. This is this full screen one, I think, that I did. Yes. So here you don't have the black square. Okay.
No, that's okay.
Okay, so we can do anyway.
Awesome.
Do I leave it there or I stop sharing or?
Well, I think no. Actually, maybe we'll go back to that later. So I don't want. We're gonna discuss that, but I don't know when. So maybe you can share it later. Yeah.
Okay, so I stop sharing.
Yeah. Anyway, it's gonna work. So that's cool. I think probably there's gonna be some questions about the last week presentation you gave, but that mostly I think people are going to discuss the exchange you had in the email and what's gonna follow.
I think there was an email by Carlo just a few
Yeah,
10 minutes ago.
I read it. If you want to take, if you still have time. If you want to take your time to read it. You still have 5 minutes, 10 minutes. So take your time.
Mia sorella ha scoperto per caso una su internet. Non mi piaceva.
Hola, Patrice.
Hello, how are you?
Good. How are you doing?
Good, good. The climate here is crazy. It's sun and then it's cloudy, and then it's sunny and then it's cloudy.
As far as I can see, basically it starts raining whenever I am done with working. That's how I'm at working Grenoble.
That's the rule then.
Yeah, exactly. Ciao, Giuliano.
So for the good of everyone,
Oh.
you should not finish working.
Exactly, for everyone. Yes, that's ciao. Well, that's basically what's happening. So yeah, you're welcome. You all. I'm gonna have a coffee. I'll be right back.
Yeah.
It is recording, right? Yes, it's recording.
We don't quite agree with Carlo.
Hi, everybody. Hi, Alexia.
Ciao, Carlo.
Hey.
Oh, you're outside. You lucky.
Yes, well, but you see, I have a jumper, so it's not
Okay.
paradise yet.
Where are you? Where?
Look.
Oh boy. Oh, you lucky girl. Where?
Yes.
Where's that?
In Chartreuse, which is a mountain just above Grenoble.
Oh yeah.
So
yeah, I know. Grenoble is fantastic there. Yeah.
Yeah.
I was there for some time. It is
I saw you answered my remark on relativity and relativism and stuff. But it came from the guts because I was a victim of relativism, of cognitive relativism at some point. At some point, nothing had meaning anymore, and I had to have internal reconstruction. So I'm aware of the danger of this thing, and I mean, I think we scientists need to really think when we introduce a new word about the potential impact on people who don't really master science. But I agree that relative, we shouldn't be scared of using it. It's not the same as subjectivism, or because I could read sometimes that thermodynamics is subjective, for instance, which, I mean, it's super dangerous. You put this in the end of Donald Trump and that's over. So yeah, sometimes people want to make the buzz, and it's not good at all.
Yeah. On the substance, I'm 100% in agreement with you, of course. Yes. Yes, the confusion is dangerous. In fact, I'm immersed in a discussion about relativism in thermodynamics, which is exactly parallel the same lines. Because
Okay.
yeah, because there are some philosophers like David Albert that say, let me put it simple, entropy is just you know, you have a macro state of a system, and you have to be able to say what is its entropy. And there are others, which I think are right, that says, no, not at all. Entropy is not a property of the microsystem, it's a property of microsystem and a set of macroscopic variables, if you want.
Mm-hmm.
So it's a property of a set of variables treated as you can manipulate them in thermodynamics.
Yes.
And the answer of David Albert is, but this makes it subjective. No, it doesn't make it subjective at all. It's zero. It just so if you have a gas of two, I don't know, oxygen and hydrogen mixed, there is an entropy if you distinguish the two, and an entropy if you don't distinguish the two.
Mm-hmm.
But that doesn't make it subjective. It's just an entropy function of the chemical potential, and one is not functional chemical potential. So I see the danger of, but I think it is the way out is to clarify exactly what meaning of walls, and say there's absolutely nothing subjective in entropy.
Yeah. It's an objective quantifier of ignorance.
Yeah, exactly. So
yes, also Carlo, in your last answer, there is something that I don't like very much, which is analyzing the quantum systems. You say A is asking a question to F, and F is answering so and so. This is really something I find misleading. There were recent experiments about Wigner's friend experiment where the friend was a photon. For me, you have to decide whether it's a friend or whether it's a photon, and it's not. It's a big choice.
Can you repeat?
My friends are not photons; they are.
Sorry, Carlo and Philippe. Sorry. First, Philippe, we couldn't hear you very well, so Carlo was asking to repeat. But I'm also asking you both to wait, because I'm guessing you're gonna start already the discussion, which is awesome. But if you can wait 2 or 3 minutes more, there are a lot of people still to come. Sorry to interrupt you, but.
Well, since Alexia and Carlo started, I continued.
Well, it was an email, so you can reply with an email right now if you like, but otherwise, please wait just a couple of minutes.
I can reply to that, yes. So for me, photons are not persons.
Let me count. I think there are Marco.
Philippe, can you turn your video on? So.
Yes, but it was telling me that the connection was unstable.
Okay.
Let's try. Okay. So as long as it works, it's fine. But actually, I have 2 computers, so I maybe try the other computer where it works better. I'm not sure. So far, it's working. Okay, we'll try to stop the other computer so that they don't fight for the bandwidth. He doesn't want to stop.
Yeah, I find that Zoom works much better, both if there's no fight on Wi-Fi, but also if there's no fight in the memory. Zooms, I mean, when I have Word and Excel and Mathematica open on the computer, Zoom has troubles.
Yes, so try to I will leave more softwares maybe. So okay, I will quit PowerPoint. I don't need.
Okay, well, I think we can start. There's still Zoe and Marco, but I think we can start, and if they join. Well, it's gonna be easy for me today because the discussion is already on, so I don't have to do anything, just leave you be. And however, since Mauro is gonna leave in 25 minutes, ciao Mauro. I thought maybe if you have comments or questions, we can start from there, and then when you have to leave, we're gonna keep going. Mauro?
Oh, I don't have questions, actually. I want to listen.
All right, no, that's okay.
Not now, not now.
Honestly, when I saw the bit in the email exchange on the unitarity, I thought you would have, attacked at some point, but maybe you will.
No, I want to listen to Carlo.
All right. Well, then let's do that. So first, Philippe wanted to, rightly so, reply to the last email from Carlo. So maybe we can start from there, and then I'm gonna ask you the questions that some people sent me, and also Hippolyte, who unfortunately is not here. Ciao, Hippolyte, when you will hear this recording. Get well soon. And please, Philippe, you can start.
Oh, well, it was very informal. I was just saying that, but it was sort of a picture in Carlos' email that F is asking, F is a friend. So it's sort of the meter and S is a system. And so they are asking questions to each other, which is sort of a relation. But I don't like that kind of picture where you personalize quantum objects. And especially, there was a little bit of a controversial recent experiment, which was a Wigner-Friend experiment, where the friend was a photon. So obviously, with photon, you can get entanglement, you can get everything. But I think this is misleading, as you can guess, because this is what I wrote in one of my emails. You have to choose whether you are context or, well, I use adjunct because it was related to, for instance, Renato's Renner thing. He speaks about adjunct. I don't, typically in CSM, we don't speak about adjuncts, we speak about context. I agree that I avoid speaking about adjunct because adjunct comes with consciousness and all kind of stuff like that I don't like at all. But still, for me, a context, the photon is not a context. And I think this is a main discrepancy with Carlo in some sense. That it also appeared in an email by Alexia. That is, it's not the same thing. We put this difference between context and system, and you cannot freely shift from one to the other. And if it is a system to another system, you get entanglement. If it is a system to context, you get measurements. So
actually, to
yes.
To complete Philippe's comment, so I guess we are going to discuss about the text you sent during the week from scratch here. There is no initial presentation. We start like this. So when I read it, I wanted to ask you, how do you define a fact, actually? Because in CSM, I mean, the facts are these repeatable phenomena where we can have intersubjective agreement, etc. While here, I have the feeling it's more related to what we know about quantum state. So how do you define it?
Especially a relative one. I still miss your relative facts because for me, what is a fact is that, for instance, S and F are entangled. This is a fact because as a context, I can check that they are entangled. But between them,
Okay, so here I clearly did not understand because for me, a fact is the repeatable phenomenon. It's the stuff that can bring agreement. It's not that it is entangled. It's
no, but being entangled is a fact with respect to the context. For instance, if you prepare a singlet state, for instance,
okay, I get that.
The singlet state is a fact because you have a context which is able to make a Bell measurement, and which
but that's not the phenomenon then.
No,
that's the modality.
The modality, yes.
Okay.
But
so we are trying to guess, but Carlo did not answer because
yes, we both of us trying to guess what is a relative fact, but okay.
So no, I understand what you say. I understand that you by fact you mean something different. So I understand that. I think I understand what you mean by fact,
But
I think that
our facts, sorry, are your stable facts. If you take as facts your stable fact, I think we agree. But
yeah.
the trouble is a relative fact that we don't grasp.
Yeah, exactly. So I think you're completely right. So I think your notion, the notion, what you call fact is what I've called stable fact in that.
Yes, I think so, yes.
Yeah.
Now, what is a fact? I think this is a very good question. And Alexia, you mentioned something like repeatable phenomena.
Mm.
And good. So let's take the notion of repeatable phenomena. And I think that the notion of repeatable phenomena has two connotations. First, that it's repeatable. And second, which is a phenomenon. So let me separate the two. One, repeatable means that, I'm not sure what it means. Let's put it on a for you is important, of course. But the point is that there are phenomena which are not necessarily repeatable, or just phenomena. So the question, what is a fact? In my opinion, the way I'm thinking now is that we have a mathematical theory which we agree upon, more or less, type 1 quantum mechanics, the way you call it, quantum mechanics, quantum theory. And then we have the world around us. And we need a link between the two. We have to say which part of the theory we take it as realistic. In a sense, we want an ontology to connect it to the world. Now, we all disagree in this, at least the people who are vocal among those who are in this Zoom meeting, that it's not a good strategy to say, okay, the wave function is the reality. That's what is really happening, and all the rest has to reconstruct out of the wave function sort of magically, like it happened in many words. We don't think that that's a proper way of going.
Yes, we agree on that.
We don't like that. So we agree that this is about phenomena. Mm-hmm. And when you said repeated phenomena, you said phenomena. Now, I think that a good way of thinking about the world is thinking about phenomena, things that happen. And this, I would say, let me separate the meaning of classical, because we are sometimes, I think there is a little bit of
there are too many classical.
Right, there are many things in which classical. Bohr was saying something like, we all use classical concepts. This is a very wide notion of classical, right? And I agree with you that, and I think you also use the same thing. So what quantum mechanics is about is not wave functions, it's about the LZ component of this of the spin of this particle is plus h bar half at that time. That's a fact. That's one example of a fact out of many. So within the quantum formalism, I think we can identify things which the quantum formalist talks about, which are facts, which I want to call it fact, and connect it to aspects of the world. Now, the formalist gives probability amplitudes. In fact, gives probabilities. Let me talk about probabilities, square of amplitudes. This is a probability of what? Of facts. And I want to talk about these things and connect these things to fact of the worlds. Now, of course, you can say, of course, we also want to do that. And we identify with fact with those which I would call stable fact. That's perfectly fine. I'm saying there are other facts. In the theory, there are other things to which I attach probabilities, which do not have the stability properties. I understand you don't want to call them, but they are there. They are there. If I have a particle in two slots, there's a probability of getting here and a probability of getting there, even if there's no interaction revealing that. Mm-hmm. Okay. So I would say that we can take the notion of facts as the connection between reality. Reality is an ensemble of facts. It's a Wittgenstein point 1 of the Tractatus. So fact is everything we usually call facts. the question where we don't agree is that you're saying, good, so I want fact to be stable, to be, as you said, repeatable, and therefore they have to somehow have a classical context, and I agree that they become stable when there's a classical context, and I'm happy. This defines a consistent metaphysics. So, of course, this defines a consistent metaphysics, which is different from the one of relational quantum mechanics. The one of relational quantum mechanics says, I'm not happy with this because I haven't seen the type 2 program working yet, in a sense. And and because those facts, in a sense, I expect, I may be wrong, they are all FAP, for all practical purposes.
But
you can also postulate them. Then they are not fact. They are your basic postulates. That is, you start from a classical world. This is what.
Yes. Let me just conclude. So I use what you just said, Philippe. So. Relational quantum mechanics, which is different than CSM. That's the point. I mean, somehow I think we understand one another. We should separate understanding one another to saying why we think it's more useful going one direction. The facts of relational quantum mechanics are the basic postulates, if you want, the basic object we're talking about. Reality is made by facts. Quantum mechanics describe it. They exist also if there is no classical world. They exist if there is no repeatable, and they have the property that they are labeled by physical systems.
Just a quick question: would relational quantum mechanics exist if there was no quantum formalism?
Yes, I think so. We just would.
Can you start by a phenomenology? Because here the way you define it is to relate reality and quantum formalism, while CSM starts from scratch.
Yes, 100%. And in fact, I sort of wanted to do that, not to start from the formalism, not at all. Start from the say, well, I see fact around me and blah, 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 blah. But then I was very excited when I read your papers, because it seemed to me that you do it better. So I was going to buy your language somehow. At some point I realized, talking with both of you, that I was overbuying your language. But I still am happy with the way you present it. So the way you present it, the only difference is that I think that when I, Carlo, see spin up, and I look at it, I call this a fact, but I expect, nevertheless, that my friend outside the box could, in the future, very, very wisely, and being able to see an interference effect between sort of me seeing this and me seeing something else. So I expect this to be true. So me not be classical after all. 100%. I'm only classical 99.9999%. But this has nothing to do with the formalism. So I expect the facts not to be stable in the sense of equation 1 of the.
Can I make a try? I can make a try. It was a little bit written in one of the emails. So it's related to CSM and also even to more very standard, even in von Neumann type of thing. When you make a measurement, there are typically 2 steps, QND measurement. I published Nature paper on QND measurements. Well, what you have first a system and then a so-called ancilla or meter. And then you first entangle the ancilla and the meter, and you get an entangled state. And then typically you extract the ancilla, you look at the ancilla with a counter, so it becomes macroscopic. You get the projection postulate, and then you know the thing. Now, it means if in the CS, so it's this paper that we wrote it's in entropy with where you have this what we call virtual change of context. So if you also take a Stern-Gerlach experiment, the first step in a Stern-Gerlach experiment is entangling the motion and the spin. So you get up, spin up, and down, spin down, for instance. But this is still reversible. So you can still reverse it and go back to the initial thing, or you can put that inside an interferometer. And as long as you did not actualize the thing, that is, as long in our language, as long as you did not connect to a real context, which goes with irreversibility, so then you can go back. So we call that a virtual change of context, and it's basically entangle different degrees of freedom. And so is it possible to understand your relative facts as saying, basically, this kind of stuff exists? Which is what we call that standard. I think Frank Lalauet would call that a pre-measurement state. Yeah. The untangling has taken place, but not yet to actualization. And so, as long as you did not went up to the real, what we call context, the stuff is still reversible, and you can get back to, and then you basically decouple your system and your meter, and you are back in the initial state. And this is possible as long as the actualization did not come up. Now, in our point of view, you can do that as long as you are at the system level. And precisely the context appears when you stop being able to do that. So we call that virtual change of context. So it's in some sense a change of context which has not been actualized. So if you have a virtual change of context, actually the modality remains the initial one, because you can go back to it at any time. So you have an initial modality defined in an actual context. Then you get the entanglement. For instance, you split your photon or spin. You have this entangled state, which is a pre-measurement state or whatever. You can still reverse. But then if you do the real stuff, you cannot reverse anymore. And this is when we speak about context, then you have a new modality in the new context. For instance, now you know the speed is up. We can forget about the down one. So is your relative fact, in some sense, claiming that this kind of pre-measurement states exist?
Yeah, I agree 100% with your picture of the situation and your reading of what is relative facts in terms of your virtual change of context. In fact, you sent me the link to that paper. I read that paper in the meanwhile, and yes, exactly, the two notions, and your description of what happens. Of course, I agree in a measurement. Everything. Let me just say how I would describe it in the larger facts that I've used, just a little bit more on what you said, but I think you're going to agree. There are three phases, I would say. The system get entangled with a meter, as you said, and this is when there is a virtual change of context, and I would say there is a relative fact of the system with respect to the meter. But in a sense, so far, it's all quantum. We're all in the quantum, okay? Then there is a second phase where the apparatus, the meter, or if you want the pointer variable of the meter, let me say into ways, interact with a quantum context, with an infinite number of degrees of freedom of its molecules of whatever. That makes the thing stable. It's not when the apparatus interact with me, the observer, that a stable fact or a fact in your sense comes in. Is when it interacts, and I would say, but perhaps you disagree here, that the key thing happening here, it is the interaction with many degrees of freedom, because it is an environment and a lot of information is lost there. So with respect to me, external, that information is lost. So now it really becomes classical. The relative fact became stable fact, because not having access to the environment being the infinite number of degrees of freedom correlated to, now it really, from a superposition, we legitimately go to either one or the other. There's no interference anymore. And that's the second phase. And the third phase, so now the fact has become stable with respect to me who am ignorant about the environment. And the third phase is the observer who looks at the apparatus. Now we are in totally classical world. I see the pointer here, and since it's correlated to the other one and now it's stable, I say the electron is there. Now the difference is that the two, I would say. First, you don't want to talk about facts before there is anything classical, and that's a choice of where to put the ontology. I understand it. And the second, you want to say it's an infinite number of degrees of freedom because somehow de facto this is not quantum mechanics. It's a variant. It's an infinite dimensional version of quantum mechanics. The question is, if you buy the ontology of relative facts, isn't sufficient Zurek decoherence for stabilizing these facts with respect to the observer? That's the suggestion in plus, but
well, but then it's almost exactly usual Copenhagen quantum mechanics. It's what you tell. You untangle, and then it's untangle, and then either you go to many worlds, but you don't like that. So you simply invoke loss of information. You trace out degrees of freedom, and then you get basically a diagonal density matrix, and you are happy with that. But this is exactly standard quantum mechanics for me, if you do it this way.
Yeah, it is standard quantum mechanics, exactly. But the problem with usual quantum mechanics is that, it seems to me, is that textbook quantum mechanics, if I read, I don't know, Messiaen, I studied on a Messiaen, on a French book, and Dirac, and is that it says, well, there's a quantum system, there's a classical world. The classical world is given. And it says, in a sense, standard quantum mechanics is much closer to what you do. The facts are only the ones when you interact with a classical world. And then my problem with that is, but wait, which is, I understand is probably you don't want to address in these terms, is wait a minute, everything is quantum. So how I have to accept the existence of a classical world to start with before start talking?
Yes,
Now,
so the idea is to let the classical emerge from the quantum. I mean, it's really the flavor of Zurek's approach then.
Yes, it's all based, like you always, this is what I discussed with Zurek on this issue. So this is a very difficult word, but I tell it. Zurek called it, he wants to be reductionist. That is, he wants basically to do what Alexia just said, to get the classical from the quantum. And what we say is that, no, you will not make it. You cannot get the classical from the quantum. You can get description of both, but you always need both. And all this idea of getting the classical from the quantum, I think it is really a dead end, and people should have realized that. But there's something that's something, well, it does not work. We know that it does not work, and even founding fathers told us it does not work. You have to make a sort of a joint description, and you can do that with type 2, type 3 algebra. If you don't want to make a joint description, just read von Neumann, apply the postulates, and you are okay. But
I have a small question there. So, Philippe, do you see your approach as being non-reductionist in a way?
Absolutely.
Yeah. Well, it's the trouble is
that's what I've been saying for a long time.
You have to be very careful about that, because reductionism is a little bit like holism. Holism is a terrible word because it can mean anything and it's contrary. For reductionism, it's the same. So we are, Alexia and we agree, we are against classical reductionism. I gave an example in the paper. For instance, if you build a house, classically, if you know the position of all the bricks, the house is defined. This is what I call classical reductionism. So we are certainly completely against that, which is meaningless in quantum. If you think about quantum computer, you can know the position of if qubits, you would have no idea about the state of the computer because it's an entangled state. So you cannot define the thing from its part. This is a basic lesson from Bell's inequalities from everything.
Philippe, I agree with you, but let me. But you're saying two different things at the same time, and that's. I want to disentangle the two.
Yeah, yes.
So when you say strongly, you cannot derive the classical from the quantum, I am 100% with you, and that's exactly what I've been objecting to the many world people, to Zurich, to a number of people like that. You and let me put it in a different way. You cannot derive. There's one way of putting this, the measurement problem, is to start from the classical postulate, you know, the 5 postulate or whatever of quantum mechanics that you find in many textbooks, and say, oh, there is a tension between the unitary evolution postulate and the projection postulate, right? That's one way of presenting the thing. And a lot of people say, oh, good. I believe in the unitary evolution postulate, that's quantum, and somehow I want to derive the projection postulate out of that. I know, using the coherence, using stuff, using many walls, using, okay. There's a huge, there's a large part of the community that want to do that.
Yes,
I agree with you, it's not gonna work. It's not gonna work. I've been debating with
agree on that.
I've been debating with David Wallace, with Saunders in Oxford, with Tegmark, with Sean Carroll. They say, oh, come on, we start from the Schrödinger equation, and then blah, 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 we are going to the fact of the world. It's not going to work. I understand.
It's applying the physical statistics program, the statistical physics program, sorry. It's emergence, and it works for some sort of randomness, but not for the other one.
But wait, let me finish. That's the part I agree. Okay. But there is another sense in which classical can emerge from quantum. I don't think that the solution of that is only, so one solution of that is to say, all right, sure, there is a classical thing, a classical world and a quantum world. There's a classical object and quantum object, and they are just primary. I think there is a second possibility, which is to say that the two postulates, the unitary evolution postulate and the projection postulate, are both correct. They only refer to facts relative to different systems. So I think that classical, in the sense having a specific value, a variable has a specific value at a certain time. Classical in that sense has to be primary. That's what the theory is talking about. So we can start from classicality in that sense. Variables have specific values. There's no wave function superposition. This is in the formalism. That's in the language. I've never seen a superposed thing. Have you seen a superposed thing? I mean, where is this superposed thing? People ask the question, why I never see superposition of microscopic object? Well, you're not supposed to. Why I never see a superposition of an atom either? I see interference. I see effect of what I call superposition. So,
you know, my PhD thesis was on single photon interferences, so I've seen some superposed photons in some sense.
No,
but
I know what in some sense, but one has to say in which sense exactly. So it seems to me that so I'm 100% with you with what you think you mean, but nevertheless, I don't think that this means that I think we have to start from classical facts, classical in the sense of
non-contextual.
No.
Stable.
No, not in that sense. In the sense that we're not talking about wave functions, we're not talking about states, we're not talking about superposition, we're talking about facts of the world. Variables having a value at some time.
But these values could be relative to some other.
And if these variables are relative to them, suddenly the tension between the two postulates disappears. Because at the same time, a value can be realized. So a classical fact in this wide sense can be realized for a system and not realized for another system. And then there is another sense in which I can derive the classical, because the classicality is the stability of the facts. A subset of facts with respect to me behave as in the classical world Namely, I can forget, they are repeatable in some vague sense, as Alexia said at the beginning. I can give them for granted. I don't have to say, oh, but that was relative to that and not to me. It just happened. I can delabel it, can delabel. So classicality can be seen as a emergent, FAP emergent part of quantum mechanics, but not of quantum, not of the wave function or the formalism, of the facts. That's a perspective. I don't want to sell this perspective. I just want to clarify that there is an enormous amount of common language that we have. We're talking about the same thing. We're talking about.
I have a question to you because you asked us a question last time, which was what makes that the context is a context. And so actually, Alexia, I did not give an immediate answer, or it was a little bit complicated. But I think Alexia gave in one email a very clear-cut definition of a context. A context is a context because its properties are non-contextual.
Yeah, that's how would you call Philippe? How would you call the non-context, which is what you use in that paper when you said virtual change of context?
Virtual change of context.
Yeah. Yes. So if my spin interacts with something else and the interaction involves a certain context, but it's not a context because it's not classical yet. Would you have a name for that?
Entanglement, yeah. What we get between in a Stern-Gerlach in a so-called pre-measurement state in standard quantum mechanics is an entangled state actually. So you build up an entangled state. You entangle, for instance, the spin and the position in a Stern-Gerlach, or you entangle a signal particle with a meter particle in a quantum computer. And then you get an entangled state. And this
Philippe,
yes.
I think you are not obliged to go to the entangled step. Actually, we can think about a change of context for a simple system, and in that sense, I would call it a coherent superposition.
But it's the same. It's another way because if you, for instance, if you split a photon, you can either see as a superposition of position, or you can see it as an entangled state, which correlates to properties. For instance, for a polarized photon, you go to a polarizer. So if the polarizer like that, so either the photon goes this way, so you correlate, you entangle actually the position and the polarization because on the two paths, the polarization are crossed. So I think it's always a question. It's a question of definition of modes, but you can always rewrite superposition as entangled state between different degrees of freedom, not between different particles, but typically between different degrees of freedom of the same particle.
So but you want to take Alexia and not talk about the formalism, not talk about states, not talk about, just talk about.
Yes. So
primary logical notions and not.
No, but as I said, so yes, this is an important, we had many discussions with Alexia about, you start from a modality. So a modality is something which is reproducible in a given context. Now you can go to another context and you will get new modalities, always the same number of modalities for a given system. Okay, so this is fine. This is a standard projective measurement and blah, blah. But now, if you want to go to this sort of mixed position, this was done already. This is the idea of QND measurement. You know, I wrote many papers on QND measurement. It's a two-step process. I discussed with Braginski, with also many people. So what you do typically is that you have a system, and you first entangle this system with a probe. So a probe can be another degree of freedom of the same object. Actually, it can be spin, position, and blah, blah. You get this entangled state, and typically you extract your probe and you make a projective measurement or irreversible measurement on your probe, and then you get the new state. So
well, that's Gerlach is a prototype of that, right? Because the position.
You may not like it. You may actually change your mind. And then you can reverse. And since everything is entanglement and disentanglement are unitary processes, you get back to the initial state. So in our point of view, you always, where is the certainty? For instance, the split photon, where is the certainty? The certainty is where it comes from or where it will go if you recombine. So you still have modalities, but it's modalities which is not, which is in another context. So what you usually tell with Alexia, that what is a quantum superposition? Quantum superposition is a certainty in another context.
Is a certain?
Is a certainty in another context. Because, you know.
Sure. It's a, sure. I would say it's a definite prediction with respect to a third.
With respect to another measurement, which is not
the measurement, which is
hanging around. You know, you have your split photon.
Sure.
The split photon does not know where it is, but it knows for sure that if you recombine them, it will go this way and not that way.
Right.
So
Yes.
this is why we say superposition is a certainty in another context. And then as long as you did not actualize, that is, you did not couple to some sort of very large.
Just to probe you, Philippe and Alexia, suppose I am God and I create a new universe, not ours, which has many degrees of freedom, but a finite number of degrees of freedom. Okay, and is ruled by quantum mechanics, whatever quantum mechanics is. Would you say that nothing ever happens there?
Oh, this is very dangerous. I don't know. There are also issues, for instance, if you allow me to show about the Cohen-Specker theorem, for instance, I had big discussion with Adam Cabello about that, which is in Gleason's theorem, in order to get Born's rule, it's absolutely essential to have a continuity of context. The context is continuous. Okay, this is essential for Gleason's demonstration. Now, if you do Bell's inequalities experiment and blah, blah, you have only a finite number of contexts. Like you have this, that's 4 contexts for Bell's inequalities. For Cohen-Specker, you can go have many contexts, but it's always a relatively small number of contexts. So now, can you get Born's rule if you only allow a finite number of context change? So I tried, I did not, so Adam Cabello told yes, I did it. He told he did it. Actually, he's not so sure anymore. I got some criticism. So it's a little bit shaky. So for instance, it's unclear to me that you can, if you are God, that you can get Born's rule if you have only a finite number of contexts. I think the infinity of the number of contexts, the fact that you can move, your all 3 states, the 3 states can move continuously. This is the spirit of Gleason's theorem. If you only allow this one and this one and this one, will you get Born's rule? So far, I was never convinced. So I had so Cabello tried to do that based on graph theory with very esoteric theorems. He told that it succeeded. I think he stepped back a little. And so I told him many times, Adam, what you are trying is just a discrete version of Gleason, and Gleason gets it, but for continuous. So why do you want to make discrete version of Gleason, which is sort of pointless? But well, we disagree.
I don't want to make a discrete.
Yeah,
whether you think that reality only comes in because there are infinite numbers.
I just want to come back to your question. When you say a world with finite degrees of freedom and quantum formalism applies, but it's a complementary answer to what Philippe said. I'm really not sure that the quantum formalism should apply to a finite degrees of freedom.
Or of context, well, yes.
So
for myself, I cannot demonstrate Born's rule, or otherwise Gleason's does not work if I don't have a continuous context. So in our postulates, axioms of CSM axiom, we do add the fact that the context change are continuous because you need that for Gleason. And so, all these people doing GPTs and things like that, they always start from Cohen-Specker or Bell argument, and they always start from a finite number of contexts. And I think they're stuck in a dead end. They are stuck in a dead end because contexts are not discrete. They are continuous. This is the basis of
the reconstruction. I mean, forget the reconstruction of probability from Born rules from just let the theory be whatever it is, independently of the reconstruction.
No, but it's important because we can't I mean, we question the mere thought experiment that you suggest, because with a finite amount of degrees of freedom, we are not sure that we can have any unitarity, Born's rule, whatever. So we don't know what to start with. We have neither the phenomena nor the mathematical formalism. So basically, I'm like,
we are God, so we try being God, and so
you're saying what everybody missed so far in the discussion about the interpretation of quantum mechanics is that's your main point. There have been 100 years of discussion of quantum mechanics, but everybody missed one point. And the point is that quantum mechanics in the strict sense does not apply to systems with a infinite number of degrees of freedom, which are generally different, or generally classical, and that's the classical world of Bohr. That's what you're saying. And then you're saying, and using type 2, maybe we can do that concretely, because this is an open...
Well, it's still open, but actually I did not invent that. I think it was, I think von Neumann understood that in 39 in this paper.
No, von Neumann understood that you need those kind of algebras perhaps, but never suggested that this has to do with the measurement problem.
Not so sure.
No, it's a new idea. Yeah, it's a new idea. It's your idea. It's not von Neumann idea. It might be very interesting.
It's not written in von Neumann paper, but you know, if you the story, if you read a little bit of history, von Neumann was extremely rigorous about anything he wrote in a paper. But in letters or in discussion, he was not so rigorous.
Well, maybe phenomena suggested that, and very few people have noticed that. You have, I know there are super selection rules when you have, if you want, representations of algebras of type 2 or type 3 algebras. I don't see how super selection rule can be related to different positions of the hand of a pointer, because the point is that I don't see how the infinite number of degrees of freedom can do the job if not for the coherence. In other words, what happens at the edge of the universe, as Alexia rightly put it, is that you're forbidden to have superpositions anymore, right? I entangle my system with apparatus and then entangle my apparatus with something else, but at some point, this entanglement stops and I don't have superpositions anymore. But I don't see anything in type 2 or type 3 algebras that tells me that the unitary evolution itself it's broken.
Yeah, well, no, so it's clear that it's broken. It's what people call non-unitary equivalence of representation.
But it's the non-unitary equivalence of representation, I know very well. It's you don't go there by unitary evolution.
Mm-hmm.
Either you break unitary evolution, or you don't generate it. So if you're in a leaf in the sense of representation theory, just stay in that leaf. But you always have unitary, you don't break superposition. If you are not in superposition, you cannot create it, but you don't break it either. So I don't see how using that mathematics can help in the measurement problem.
Well, I think it can, but that's complicated because, you know, at first it's very mathematical. I tried to read many papers. People disagree. They don't all tell the same thing. They start either with von Neumann algebra or C-star algebras. The rules are not exactly the same. The theorems are not exactly the same. And then they basically demonstrate theorems. And if you try to know whether these theorems are relevant or not for physics, you have hard time. Well, for instance, this 39 von Neumann paper, the idea is pretty simple. You know, I try to explain it. So when you make a measurement, you entangle your system with a meter, and then you entangle more and more and more and more, and you go to this so-called von Neumann regression that von Neumann never told that, which is that you entangle everything with everything, and you get to many words picture. And this was especially specifically said in a famous paper by David, David, where he advocated. Everett was half crazy, and actually he gave up his idea because he went to Bohr, the story, and Bohr did not even want to speak with him. So he went to other things. He was calculating engineering, etc. And his ideas were picked up by David, and David wrote a famous paper where he sort of relaunched Everett ideas by doing based on this infinite regression. He said, okay, so you entangle and entangle, it's unitary, so it never stops. So you go to many words. So why is it wrong? I think in my mind, it's completely wrong. So this was shown by von Neumann in his 39 paper. If you take systems and if you make tensor products, so you go to infinite tensor products, so for just qubits. So the dimension becomes 2 power n. 2 power n becomes infinite like real numbers, so it's no more countable. It becomes a count. So you get something which is absolutely awful, which is a sort of a gigantic Hilbert space with uncountable dimension, non-separable, nothing, just a mess. You cannot do anything with that. So what was von Neumann trick? I will define equivalence class, which are not our equivalence class. It's other kind of equivalence class, which is basically a criterion which forbids me to distinguish two states in this huge mess. And then he gets what he called incomplete tensor product. So he gets a criterion which allows you to select sub-ensemble in this huge mess. And then he shows that the huge mess is actually a direct sum and no more a direct product of these different things. And these different things are super selected. So nothing couple them. So basically you entangle, and then there is something awful happening, and you end up in a direct sum, and the direct sum are basically mutually incompatible results. So this is my intuition of the stuff.
Yes, and one of the super selectors is the one picked up by Fock in his paper, in which you essentially you take one of the states and you just for instance in your example you take 0, 0, 0, 0, and you take all the one with a finite number of excitation over 0, and that's Fock space, which is a little corner of this huge thing.
Yeah, yes.
I agree. That's perfectly fine. But what I don't see is how by starting from one state, entangling, you get out from one single leaf. You stay in a single leaf. You don't spread from one leaf to the other. That's exactly the super selection.
Yes, but if I understand correctly this von Neumann thing, he defines a criteria which allows you to make sense of this result, which is this equivalence class. And then the equivalence class automatically creates a super selection rule. It's sort of a kinematic. That is the big entangled thing.
I agree with this. I agree with this, but I don't see whatever unitary evolution you have. It doesn't move you from one super selected sector to another.
No, but
so if you start from a state where your original finite little corner of it was entangled, you entangle, but you never get out from that. I mean, you can view this entangle as superposition of two states. There's never a case in which one state migrates to one leaf and one state migrates to the other leaf.
No, they don't migrate. They rearrange. That is, you go from this infinite tensor project to something which is a direct sum. So
no, look. I mean, think.
But everything is still infinite. That is, each element of the direct sum is basically one quantum state of your system tensor one state of the context of the.
But evolution, if the evolution is unitary, let's say you start with all zeros, and then the first one is it's in a superposition state of up and down and entangle with the next one. That's the system and the apparatus, and then they keep entangling. Okay, so you started from a Fock leaf of this huge thing you're describing. And then the unitary evolution moves you in this forked leaves forever and never goes to another leaf, exactly because of super selection.
Yeah.
So you never separate the two. You can never use the classical. The classical variable you want to use is the super selected one, the one that changes from one leaf to the other.
Yeah, yes. No, I know these things. I read the paper, and so people. This is where people start to fight. So there are various tricks to get out. For instance, if you allow infinite time, you break the rules, and but infinite time is a little bit troublesome. If you allow infinite resource, I think your argument fails. But then people tell, oh, okay, but it's never really infinite, and so it never happens, and you always are stuck in your, how do they call that? The Hamiltonian evolution. There is a basic algebraic structure of the Hamiltonian evolution, which makes that it cannot work unless you allow infinities. And if you allow infinities, people disagree on that, but I still think it works. So Bob wrote a paper.
Are we then so far away? Because at that point we are very close in a sense. Because I think I see that if you allow infinite time, in your example, I mean, all the spin, they get all excited in infinite time. You just every second one. When you have all of them, and when you have all of them, you're outside the Fox slice, right? Because Fox slice is always a finite number of them, arbitrarily large but finite. So, but then basically, we are saying the same thing.
Yes, but except that we
agree on the math. We agree on what happened physically. The only thing we disagree upon is where do we want to put the name? All right, so now let's get out of the mathematics, which we agree upon entirely, and connect to a real world. Okay, and here is a good example. I think that since in reality the entanglement with many degrees of freedom is very fast and goes all over. So this is not really, we're almost at infinity, right, all the time, because everything gets entangled, all these degrees of freedom get entangled.
So almost at infinity, in my view, is the big trouble, because managing infinities is highly non-trivial. It requires algebraic topologies. It requires theorem. It requires you know about all the norms. You can choose anything you can tell can be weak or strong or ultra weak or ultra strong, and then people, when you read paper, what you're feeling is that people demonstrate theorems, which means that they put some hypotheses and get some results. So it's nice mathematics, but if you wonder whether it's relevant or not for physics, you don't know. And it's very unclear.
Fine, but we're agreeing, Philippe. What I'm saying is that if you want to go that way, you have to say, when I make my measurement, if I really want to be a mathematician, reality comes in only when t goes to infinity.
Yes.
But we, a poor human that only live 100 years if we're happy, if we're lucky, we don't have t equal infinity to wait. Nevertheless, t equal infinity is a fantastically good approximation to that case. So why do we want to anchor our ontology to a limit when we can anchor our ontology to something which exists for every t, and then say, look, the properties that we see in the world, the stable world around that, are because we are so close to infinity in that sense.
Yeah, but this is what our context system splitting is exactly that. It's both sides of infinity. That is, the physics is that you get quantum systems and context, which are all physical objects with properties, modalities are reproducible, you are perfectly happy. Now the question is how to describe that mathematically. And so for me, I'm not sure, but from what I know, either you stick to the quantum thing and you are happy with type 1 quantum mechanics, unitary evolution, but you should apply the projection postulate, and von Neumann was pretty smart on that, or you want to unify the description, but then you have to go into this awful mathematics because you want to manipulate both sides of infinities. Also, an image that we use with discussion with Frank is asymptote. So if you make a collision process, basically you have two particles interacting and separating. So strictly speaking, they never separate. But in practice, if you do an accelerator, you are interested in asymptotes. So asymptotes is going to infinity. And
maybe not so
in order
far.
to reach asymptotes, you always need an infinite time. But actually, in CERN, what they see are asymptotes.
Maybe we're not so far. It's only that sort of you're a product of French mathematical rationalism and a product of Italian concreteness.
But can you repeat that?
If I have a glass of water, okay, I put it in the refrigerator and it becomes ice, do you think there is a phase transition there or not?
Well, this is a standard wording, yes. This is what I put.
But I'm reading in my phase transition statistical physics things that the phase transition only happens with in the limit in which n goes to infinity. The phase transition is continuity in the and my class has only an avocado number of those, so it's not infinity. But you still think there is a phase transition. How do you put together the
details? So we had many discussion about that with Roger Balian, who is a super expert on all these things.
No, we know the physics there. It's just I want to understand. We all agree. We all know what happens.
We all agree.
Your language here.
Yes. So I think it's a related process, but from discussion with Frank and Roger, they always told me it's not the same thing, and I would be tempted to agree it's not the same thing because of these very peculiar properties of quantum probabilities, which are projective probabilities, etc. But it's a similar idea, clearly, and Roger fully agrees that, for instance, so he likes to deal with phase transition as approximation. A large number of approximation, it never goes to infinity. He hates infinities. So he do it with approximation, he makes reasonable approximation, he justifies the approximation, and he gets something which is very close to a phase transition. Now the theorem tells, but as long as you are not infinite, you don't get the really sharp phase transition. He does not care. He said, okay, you can tell that, then you go into mathematical mess. You have a very complicated theorem and they are completely useless. But well, if you like it, you can do. This is more, I don't know if Frank is here, but this is, I think, a summary of, but I don't think Roger is here. It's a summary of his position. So I think it's related to quantum mechanics. That is, for instance, algebraic quantum mechanics has been used in statistical physics also, precisely for phase transition and things like that. And there are several schools. Are they really useful, or are they just for decoration? And people, it's also an issue. People never agreed on that. Roger Balian, who is a super specialist, basically tells it's nice but useless. Some people tell if you don't use them, algebraic techniques, you are incoherent. Mathematically, it's not well founded. So you see, it's a little bit of, and for the measurement theory, it's even more obscure because is it exactly the same problem? Not exactly the same problem. In my view, it's a closely related problems, but again, too tricky.
Maybe we should leave others to come in. We've been monopolizing the discussion a lot.
Yes.
And I'm sure there are other...
yeah, actually, maybe we could go back to the first part of the discussion, because I think there were a couple of questions there. One is from Giuliano, actually. And I think, there was kind of a disagreement with Alexia, between Alexia and Carlo on the definition of relative facts and facts in general. I was quite interested in that, and then we moved on. So Giuliano has a question, so maybe I think it's related to that. So Giuliano.
I was wondering whether one could adapt like a view of fact which is fairly standard in analytic metaphysics to the context of relational quantum mechanics. So there are different view of facts, but many of them agree on the fact that facts are complex entities. So they have constituents, and those constituents combine among each other in certain ways. So usually constituents, at least for basic facts, are individuals and properties and relations. So and the way, so but facts are not just collection of things, of those constituents, are ways in which those constituents combine. And the usual way to understand this, sorry for the pun, way is by something like instantiation. Okay, so that instantiation is not, again, a relation, is something different, but anyway, and it thinks to me that like ordinary facts outside of the quantum context are facts for which instantiation is simpliciter, so to say. So either there is instantiation between the apple and redness, between two things in space and being to the right of, or not. No, that's like whereas in the context of for what I read, at least in the context of what of relational quantum mechanics, instantiation is always relative to a context. And that's also for so-called stable facts. So stable facts, you say, are subclass of relative facts. So stable facts are not absolute facts like the classical facts. You know? So instantiation is relativized to a context even for stable facts. The only thing is that they behave according to a classical logic in the way they combine, basically. And so you can treat them as if they were absolute, but they are still relative. And so I was just curious to know whether this way you see the ontology of the theory is correct. So in a sense, at the level of constituents of facts, the ontology is absolute. So those are the constituents, full stop. But the way they combine to each other, so the way instantiation works, instantiation is always relative to a context. And so that's why I think you say at the beginning that nothing is completely classical, because instantiation is always relative. It's just that for certain class of facts, we can basically bracket the relativization because they behave classically. I don't know. Is that a way to capture more or less what you?
Yeah, entirely. I think for what I understand, I mean, I don't have a training in analytical metaphysics sufficient to be careful the way you are. But for what you say, I would agree with what you say. You said that the fact is made by individual properties and relations. Of course, there are very little properties, contingent properties here, because all things we usually call properties are really relations here.
Yeah.
Property relative to. So I don't know, the velocity of an object, it's a fact, but it's really a relation between an object and another object. This is the standard example I use. Now you say this instantiation, if you have to say this word, of a fact, it's itself relative. Yes, that's the core of the matter, and the way can be phrased that in the terms in clear. I mean, the way analytical philosophy is clear. That's one of the key within itself. The way can be said clearly. I am not capable of putting all the dots on the I. I'm sure, but everything you said, I would agree. And of course, as I've been said, if you go in the direction of Alexia and Philippe, you don't have to worry about this excessive relativism on the one hand. And then you have to worry about the fact of relying on this infinite limits in some sense. So it's a trade-off here between where do you want to attach your ontology to, it seems to me.
Yeah, I see.
I have a question also. So if I understood correctly, but I'm not sure I understood correctly, from what you said, a fact with insensation is what Alexia and me would call a modality, or what Carlo would call a stable fact. But do you have a fact without instantiation? I thought it would not be a fact, but okay.
Yeah, no. The point is that, so instantiation is the way the constituents of the fact combine to each other. So the constituents of the facts are individuals and relations. You can also just have the relation and having properties as a relation. One slot relation is a limiting case. So that's like, so you have individual and the relations, but a fact is not just the collection of the individual and the relation.
No,
it is
no.
individual instantiating the relation.
So you always need the instantiation to get the fact.
Yeah, you always need instantiation. The difference between, as far as I understand, the relational case or not, is that in the case of relative facts, instantiation is not something that obtain simpliciter. So it doesn't obtain just tout court. It obtains only relative to something. Whereas in the classical world, instantiation looks like it just obtains simpliciter. So if the apple is red, it's not red relative to anything. It's red, full stop.
I can hardly follow. I don't see what is an instantiation, which is not an instantiation, but probably I'm missing some.
No, but I think I see. Well, I totally agree with what Giuliano said, and I think that's why I wanted to go back to Alexia, because the impression I had was that, also reading one email from Carlo, was that a part of what you were saying was kind of attacking the very idea that we can make sense of relative facts.
No, but we are not attacking. I don't say.
No, well, I was too rude, but I think
I don't understand. Yeah, my best attempt was to do this pre-measurement state. So if we have pre-measurement, we have an entangled signal emitter, and this, for me, it's an entangled, or it's as we said, it's a virtual change of context. And when we are in this situation, then we have what Carlos calls a relative fact. This was my closest approximation, but still I would not call it that a fact, except because the fact actually is all the story before, which allowed me to prepare that. And so I'm still missing what is a relative fact, sorry.
So maybe again, that Giuliano can help me, because he knows the literature. It's modest, but he knows the literature about facts. I think so. When you were saying what's before facts, it's not really, probably we can call it the individuals or whatever properties there are, and then you can have your ideas about what properties are related, that maybe they're just relations and so on. But before the measurement, what you was calling facts probably are just individuals in a way, or the things that interacting and doing stuff can get to facts. And then you seem to agree with Carlo saying, yeah, then when we get to facts, they can be relative. So the disagreement is rather about what happens before what's relative. Am I correct?
I'm a little, no. I can just repeat what I just told. I still don't understand what is a relative fact in sense of Carlo. Given that we do agree on what is a stable fact, we do agree, I hope, on what is entanglement. So this relative fact seems to me, in my view, somewhere between, but I cannot locate it. Do you see my problem, Carlo? Or
yeah,
Philippe,
but I think the reason is that you think that if I am in a closed box and I measure the spin up of a particle, it seems to me that you think that it is in principle, impossible, whatever capacity one has to see an interference effect later on. So you consider that you take it out of the space of possibilities. I do not.
The idea of the context. The context, as I said before, as Alexia wrote.
We understand your point of view. That's that's. I mean, I understand what you mean by context. I understand what you mean by.
Yes.
So forget context for it. It's just as a concrete thing. I mean, if you think that once we see something, this is blue. The electron has gone right and left and has left a dot. Then it is forever impossible to see any in the future with whatever, if I could be able to trace the photon going out, look at all the atoms, impossible to see any interference effect between this outcome and the other one. And if you think that this is impossible, then that's it. We have a different view of the world. We expect something different about reality. I think, I may be wrong, of course, but I think that it's always, in principle, possible with sufficient
control
capacity to see possible interference effect in the future. Therefore, all the concrete things which I concretely call facts in my life, they are not exactly stable facts.
Mm-hmm.
So you think it's all reversible?
Yeah,
I mean, the key point is reversibility versus irreversibility. Is a measurement reversible or not?
Sorry. It's all reversible with respect to the external observer, not with respect to me. I am not going to see interference effect between this blue. Once I've seen blue, that's it. I cannot reverse it. The fact with respect to me that's it. So the projection postulate, it's correct as it is, but it's relative to a system, not relatively to everybody else in the world who can have more information, who can measure things more.
Carlo, according to you, strictly speaking, there are only relative facts.
Yeah.
Sorry, I missed it.
Strictly speaking, from a fundamental ontological point of view, there are only relative facts in Carlo's views, as far as I understood it.
Mm-hmm. Correct.
That's a big difference with Philippe and Alexia's view.
Correct.
Where there is this fundamental distinction between relative or stable facts and then the others.
Yes,
contextual and non-contextual.
Correct. We agree on everything. We agree on the mathematics, with the interpretation, we agree on everything. The only thing we disagree is what we want to call the ontology of the theory. Do we want to call the ontology of the theory a very large set of things, which are relative facts, or a limiting case?
It's not
epsilon.
No limiting. You know, it's jumping on the asymptote. As I said, when you have your trajectory, you jump on the asymptote. And I think that it's exactly, for me, it's exactly that's infinity business. And I discussed that with, again, I think I didn't see Frank in the list anyway.
Frank was there in the beginning.
But he left? Yeah, okay.
Yeah. But he never says anything. Maybe it's, I don't know if it's Frank.
But Frank is not here.
Someone
Anyway.
pretends being Frank, I guess.
So Frank tells me, for instance, infinity has to be a limit. So you can only approach to infinity, tend to infinity, but infinity is a limit which should be reached continuously. So you can go closer. It's sort of thing you never really reach, but you can get closer and closer. And this is what he calls infinity. This is what we learn at school. But if you go to all this, algebraic business, even in von Neumann puts this Aleph, counters Aleph 0, Aleph 1. So it's transfinite. You jump on the other side. So now you are within the infinity. And once you are within the infinity, the rules have changed. And this is my view of the thing. So this is not, but this is only on mathematics. On physics, you know, it's huge number. If you take 10 to the power 10 to the power 23, I have absolutely no idea of what this number means. It's just meaningless, but it's a practical number. You just take, you know, a macroscopic number of spins is 2 power 10 power 23. So what does that mean? I have absolutely no idea of what it means. But if I want to deal with that kind of stuff mathematically, I just jump in the infinity. And mathematics tell me, if you do that, if you mathematically jump on the other side of infinity, then you are in another world. It changed. It doesn't work the same way. Everything, all you get macroscopic observables which commute with everything, you are sort of fine. And you get what you want. So, okay, so it's just mathematics. And people answer, but there is no infinity in physics. Okay, yes, but it doesn't matter. I want a mathematical description. So mathematically, I jump on the other side of infinity. I am in an infinite number of, you know, I discussed also with Masayoshi Ozawa. He told me there is something which is called non-standard analysis. I have no idea of what it is. But you just take an Aleph, you know, an Aleph is a transfinite number, and you add another number. So it's a completely meaningless. You have a finite number added to an infinite. But so I have no idea. I don't want to tell that it's the right things to do. I just want to tell that you can introduce in mathematics something which looks like the cut, something, the transition between context and system. And this thing is jumping into infinity. And then infinity is not the limit. It's a limit you can cross. You cross the mirror. You go on the other side of infinity. And this is mathematically meaningful, sorry. Cantor invented that, you know. You can make Alephs and power of Alephs and all kind of stuff. So there is mathematics beyond infinity. So, but physicists refuse that. And I think this is maybe a big trouble. This is my view of the thing, partial view. But you see, so in some sense, I agree with, so Carlo, you tell, okay, you never reach it. I say, it depends whether you speak about physics or mathematics. Physically, okay, in practice, we are not in superposition. We are here, we have only one world, maybe that world, we don't know, but we have to deal with it. But this is physics. In mathematics, how can we reproduce that? So I say it seems to me that there are tools in mathematics we can do that, but then you have to manage infinities. And then if you accept that, then you jump on the asymptote. But
am I correct? Am I correct in understanding you that you are looking for mathematical tools that can describe this fundamental cut or splits in nature, which you think is fundamental?
Yes.
But you think they are not the right mathematical tools yet?
I'm sure that type 1 quantum mechanics cannot do that. It's like, you know, being on an hyperbola and wanted to be on the asymptote. It's just impossible. So, but you can also describe the asymptote, but you have to change, and it's well known, as I said. So type 1 quantum mechanics, the standard quantum mechanics with unitary evolutions, simply cannot do that. Everybody is convinced, everybody agrees on that. So then what should we do? So there are many possible answers. So, and I think there is a sort of strongly discussed answers, which is this algebraic stuff. But the algebraic stuff is, I try to read many things, but it's still confusing. It's just, it's an idea. I cannot prove it, but I say, in my intuition is that there is a very good fit. It just do what I would like it to do. But
sorry, I have a question to pose very quickly. Oh, sorry.
Yes, somehow, Philippe, your argument is that because we do have the mathematics that allow us to jump on the asymptote or to go to the infinite, yes, then it should be possible physically. Is that kind of your argument?
It's already the case physically. This is what we see between context and systems. You know, if you speak about physics, I can make some physical axiom and tell, okay, if I want to do quantum mechanics, I need context and systems. But then people tell, okay, but context don't fit in a unitary picture. Sure, they don't fit, doesn't fit in a unitary picture. So I want another picture that's the type 1 stuff. And if extend the picture to more complex mathematical structure, then I can put everything in. And it's not emergent. Again, you don't tend to infinity and get a classical world. From the scratch, you need both to make sense of things. Which we can take.
Yeah, I guess we are not discussing whether it's possible at all to do that, but more whether it should be in the ontology or not.
No, again, you have to distinguish a physical ontology, which is some of pictures, description of the objects and relation in the world, which is physics, and how you describe it. I have a slide on mathematics. It's strongly there. I have many discussions. It's strongly dependent on how you see the relation between physics and mathematics. That is, you can either say that the language of nature is mathematics. Anything you can be relevant about natures are actually equations. The language of the universe is written in mathematical, and the laws of the universe are basically mathematics. Then any kind of stuff you can put about object is meaningless. Actually, the only thing which matter are equations and experimental result, observation. There is nothing between, all it's just meaningless extrapolation. So it's a possible point of view. I call that a Platonistic realism. The reality is in the mathematics and in the facts, nothing between. Or another way to tell is that whatever we do, we imagine a description about what the universe is, and mathematics are a tool that we use to describe this physical reality. So mathematics are a language. It's an extremely sophisticated language. It's able to make prediction, but it is a language, and it is a language that we can improve. When we invented, differential equation, we got Newton's law. When we invented algebras, we got quantum mechanics. When we invented tensor product, we got general relativity. But all these are languages, so very sophisticated languages, which allows us to speak about something. What something? The something is sort of moving. But our conviction for this is what I call physical realism, is that there is a something. And in time, we improve the description of this something. So something, sometimes the something becomes very, very blurred. So in quantum mechanics, it's a real mess. You lost your something. So what we are trying is to re-establish the something. This is what we call the ontology. I'm not sure it answers your question.
So there was a question from Richard, but first I have a very naive one. So I was wondering if I got what you were saying now correctly in response to Cyril and Vincent. I was wondering, so would it be, would you think that once you achieve this goal, the goal of finding the cut, where the cut is, in the way you suggested, would you think that then the ontology whatever ontology you would find would agree with the ontology that Carlo is suggesting? And if you disagree on that, what would you think would be the differences between them? If it's in extension or if it's in,
My physical ontology is CSM. I don't think it will move unless something really new happens, because it fits with quantum, it fits with everything we know presently. So I'm fine. It does not fit very well with the mathematics, so this is why I would like to improve the mathematics. And once I've done that, I have absolutely no idea of what will happen. That is, I will sort of answer my current question. And the science is, once you have answered your question, if it was an interesting question, a new question appears. This is how it works. If it was an uninteresting question, well, it stops. It goes to the museum, as we say. But I cannot tell more as long as I not reach my goal, I cannot tell what will happen after. This is.
But the point is, maybe these algebraic tools might help you to characterize the ontological distinction between context and system in CSM. Would you agree with this?
Yes. This is the idea. Yes.
So then it's a big difference with Carlo's view.
But then you know from now that it's going to be different, because we know from now, even without achieving your goal, we know from now that what Carlo is saying is that the facts are relative. So the world is made of relative facts, while you're saying, no, that's not the case.
Yeah, but if I may advocate for the first versions of CSM, there is already an added value.
Yeah.
We don't need to reach the type 2 algebra and demonstrate that there need to be a cut between system and context so that there is an added value, which in my sense is randomness and the induction of quantum formalism.
So I like very much one of the initial email by Carlo, which is what he calls the conceptual price. I think it's at the point where we are, for instance, if you take cubism, De Broglie, Everett, etc., there is no way to discriminate them experimentally. The only way you can separate them is by the conceptual cost, how crazy they are and how promising they are. And then people bet. You know, Chris Fuchs bet that the future is cubism. I don't follow him. So you have to bet because you basically you don't have a real problem in quantum mechanics. There is no real problem. So, but still we are not happy. So okay, this is the rule of the game. So we imagine things, and we try to make some hypotheses, to go in some direction, and to see whether something comes out. This is the usual way it works.
And there is another difference is about future avenue for future research, and quantum gravity is an example. That would be a big difference.
Yes.
CSM would make no sense in a quantum gravity context.
I don't know. Presently, yes, I have no idea. That is, I try to think about that. I could not really. No, CSM would slightly tend into the direction that gravity is a macroscopic phenomenon. So trouble is the following, but let's be more serious. If you want to have, in my view, real effects mixing quantum and gravity, general relativity, obviously, you have to go to the Planck scale. And the Planck scale is very, very far, one, almost unreachable. And two, if you go to the Planck scale, you lose everything. You lose all the standard model, all basically the four interaction, all these go to a mess. So you completely change world. Giacomo Moro is interested into that. Just go, for instance, Gerhard Tauf, you just go to the Planck scale or below the Planck scale, whatever it means, and then you try to reconstruct things. It may be possible. I'm not in this game. I'm in the game of semi-macroscopic physics, and I simply cannot tell anything really intelligent about the Planck scale. And since apparently everything really interesting appears to the Planck scale, I don't know. Another issue is maybe black holes, but because now we can see them, we can listen to them, we can shoot them. So it may be. So I spoke with general relativists. So can you see any kind of quantum gravity from black holes? So it also is controversial, and he said they are too big. Actually, it's not clear to me. But you see, if you want to say, I was trained as an experimentalist. So if I don't have an experiment, I'm a little bit lost. So here we have an experiment, which is very usual measurement, quantum measurement. There is no more usual experiment than that. So that's fine. But now for quantum gravity, we don't have any experiments. And so it's difficult to speculate. This is my view. But,
if there are no follow-ups, if you have follow-ups, anyone? Okay, then Lisa, yeah?
Just a comment. There is a beautiful experiment which is there's money in London done by Sugato Bose and company, based on some idea of him and Verletto Medrale in Oxford, which is a measurement of a quantum gravitational effect. It's a non-relativistic quantum gravitational effect. It's a very beautiful experiment, and it could rule out, if it is done, and the people doing it believe that they could do it in a few years, it could rule out some possibilities, and in particular, it rules out the possibility that there is a classical gravitational field interacting with a quantum matter. So basically the idea is to put a nanoparticle in superposition and another nanoparticle in superposition. And there is a very tiny gravitational interaction between the two that has the effect that it basically entangles the two. So then you recombine both of them. They were in a tensor state before, and after they were not in a tensor state. There was a spin on each of the two. You check the Bell inequalities, and you see that they are violated, and they are violated by an interaction by a mediator, if you want, that has to be quantum, because you cannot entangle things through a classical intermediate things. There's a spectacularly beautiful experiment. There's a lot of literature on it. There are all sorts of people writing on it from a number of perspectives. And there's consensus that it's a genuine quantum gravitational phenomenon, not in the sense that it probes Planck length, but it probes Planck mass, because what the Planck mass enters here in the sort of an interference effect. It's a very subtle interference effect. So there's H bar and G that enters definitely into it, and there's a gravitational field which is in a quantum superposition of two configurations. So if you want, the metric is in a quantum. So it's not just, I mean, Philippe is not on the game. It's not so exotic, quantum gravity, after all.
Yes, maybe. I'm not sure. But you know quantum gravity by orders of magnitude better than me. And so
that might be the matter of a further meeting. Maybe one day that would be nice to discuss that. So yeah, Richard, please. Sorry for keeping you waiting.
No problem at all. I suppose I have two vague points. One on the infinity point and where the cut becomes. I mean, in terms of this, usually with physicists at least, we think in terms of the limit, the infinity being tied to the limit as the end of some sort of process where you're adding things. But non-standard analysis was mentioned, and I think there are plenty of philosophical questions can be asked there about what the infinity means. And often, in fact, when it was introduced, the infinite numbers, if you like, were referred to instead by sort of unbounded numbers, which I think fits more with the ideas that are being placed here, as it's a concept that's decided. Okay, this is the position where now we are past whatever was finite, rather than being some sort of a crude limit. But my more serious question, I think, was, and it's a shame Mauro isn't here anymore, in looking at the CSM stuff and the RQM stuff and trying to get my own head around it and my own limited understanding of these things. It seems clear to me that there's a lot of discussion about interacting experiments, if you like. And you have some things are said, and then some mathematics is presented, and then there's some more conversation about it. But it would seem in the work of the sort of operational probability theories, perhaps trying to phrase some of the questions in terms of their sort of abstract experimental model setup. Because it would seem to me, if you have this classical world, or some world where you're talking about classical things, or you think you get there in one way or another, and you have your quantum description, either way, so you are positing a map between one of these operational probability theories to this operational probability theory. And perhaps things can be more formally described in this direction. Perhaps also that's a terrible idea. I basically wanted to ask what you thought of it.
Okay. Yes, I have a few slides on current speaker, if you are interested, because the question was asked last time. So if you want to see nice colors and all this stuff.
I just want to ask a question before, because I know it can take a bit of time, this current speaker stuff.
I have on the list, I have both Alexia and Leah, who sent me emails. So yeah, maybe we can leave. And I wanted to ask a very small one too. So, and tell me if there is anyone else I'm missing. And then maybe we can go to the slides. So yeah.
So who starts? Boss.
Yeah, Leah and then Alexia, or the other way around. Leah.
Okay. So it's a very basic question, just a little bit coming back to the Modelen's paper. It was just to be sure I understood that actually you're not telling that one of the hypotheses he makes is wrong. So you're not saying that the wave function is non-complete. You're saying that actually we cannot really speak about facts without considering like a classical outside context. So you're not saying that the measurement problem can be solved with like denying one of the three assumptions, but you like step away from that and give another way of viewing the problem. Is it right?
It's a question for?
Well, you and both of the three of you.
Try it, Alexia. I spoke too much already.
No, but I would say so, yes.
Okay.
So I think it would be interesting actually to, well, Lea, can you tell, so because there are three assumptions, because we read, the first meeting was, we were very few people, 3 or 4, before the reading group grown up. And so in this paper, modeling individuate 3 assumptions and say, well, in order to solve the measurement problem, you have to drop one of them. And then he classifies each solution to the measurement problem depending on which assumption he drops. And it's always a nice exercise to, you know, well, either modeling is not correct in individuating the measurement problem like that, or whatever interpretation I have in mind, I will want to check how I solve the problem. And the 3 assumptions are the wave function is complete, specify completely the state of the systems. The second one is the evolution is always linear. And the third one is measurement have definite outcomes. And of course, you know, I don't know.
But these are the assumptions also in the beginning of Renato's paper, right?
No, I don't think they're exactly the same, but unfortunately, Hippolyte is not here, so he cannot check.
Okay.
I don't think there is, well, I don't think there is the assumption that the wave function is complete there. There's definitely the assumption.
I don't remember.
No, I mean, no, wait. Alexia, your framework breaks B. Breaks the second. Definitely.
Yeah, I agree. I agree with that.
I mean, definitely.
Yeah, there is not unitarity everywhere, though, but I didn't exactly know this modeling's assumptions. So
it's a 1995 paper. I can share it with you. It's a very nice, you know, it's a philosopher of physics, but I think he did a great job in, you know, clarifying the problem and saying, you know, you have these 3 assumptions and you have to drop at least one. You can drop all of them, but you know, it's safer to drop only one because that's enough to solve the problem.
Yes, I think it's a very nice way of putting it. Another way is which one of the postulate has to be somehow. And I would say Alexia solution is the second is wrong because there is a classical context and we know when it goes wrong. It's not just wrong generically. We know exactly when it goes wrong, which is when there is an interaction, because every time there's a change of context, the second is violated. So this is CSM in my understanding. RQM, relational quantum mechanics, is no, they're all right, but the second and third are one is right with respect to one system, and this third is right with respect to another system. That's a way out. So they're wrong. The second and third, they're wrong if they're unqualified. They're right if they're qualified by putting it relative to different systems.
Yeah, that's a very nice way to so thanks, Lea. That's a very nice way to see the distinction once again, because it looks like Rovelli will, Carlo, I don't know why Rovelli now, Carlo will want to, you know, redefine the words that modeling uses into assumptions, while it looks like CSM will straightforwardly deny the second one. So yeah, that's a nice way to see the difference. Of course, if you have follow-ups, Alexia and Philippe, or we...
Well, I miss what are these 3 assumptions, so I cannot tell anything.
So the first one is that the wave function is a complete description of the physical system. The second one is that the systems always evolve linearly. And the third one is that measurement always have definite outcomes. So if you always have definite outcomes. So Everettian drops 3, GRW people drops 2, and Bohemians drop 1, just to, you know. And it looks like you dropped 2, right? Like Copenhagen and like GRW, but instead of GRW gives a mechanism for why
according to my last preprint, we also drop 1 because we tell that actually the quantum state is incomplete because you must specify the context. So it's my extravalent modalities, you remember? If you just give the projector, the psi, what you give is not a modality, it's a class of modality. It's all modalities which can be transferred between contexts. So now if you want the full modality, you need also to specify the context. I tell it in usual words. If you just give the projector, you don't tell anything. You have to give the observable. And the observable is a complete set of projectors. So you see, if you just give a psi, you just give a projector, and the projector is incomplete because it does not define a context. To define the context, you need the full set of orthogonal projectors, that is, you need the observable. So now you have to complete the psi by the whole context. So psi is incomplete, and so whatever you want. This is my last paper on the subject. But you see, it's a way to tell. Basically, people try to complete psi from the bottom. This fails. Cohen, Specker, Bell, everything is dead. It cannot work. Okay, unless you put non-locality in the okay. But if you want local hidden variable, don't work. Okay, that's fine. Now, is it the end of the story? I tell no. You still can complete, and what you can complete is to add to a given psi. If you want to be complete, you have to specify all the other orthogonal psi, which defines the observable. That is the context. A psi itself does not define a modality. It defines a class of modalities.
Extra modality that somehow goes around that. There's this extra modality, how do you call it? That somehow goes precisely around that. How do you call this? The extra modality, I forgot the name you use.
Extravalent.
Using Glasion.
Extra contextuality, yes.
Extra contextuality, that is somehow a way around this, isn't it?
Extra contextuality is the fact that I try to use standard language because everybody knows that. You have the psi or the projector. The psi or the projector define the fact that you can transfer certainty between contexts. And so it does not fully define the modality, for instance. So you have to, I make my little picture. If you think with a qubit, it does not work because you need to be at least in dimension 3. But in dimension 3, 3 modalities are 3 orthogonal vectors. Now, if I fix these orthogonal vectors, I don't determine the basis because this can rotate. And if you want to specify the context, you need to specify the 3. If I specify only one, my description is incomplete.
Right, but when you change context,
yes,
what you bring with you
yes,
is given one context and given the other context,
yes,
what you want to know to go to the next context is suffice to have the modality, not the full. That's extra contextuality. Otherwise, it's not Bayesian theorem.
Yes, the contexts are 3 orthogonal vectors, so I can orient them continuously whatever I want. And what we call extra contextuality, which is also the basis of Bayesian theorem, is that if I block this one, I can still move the other 2.
Yes, exactly. And I think that's assumption 1. That's assumption 1. So
yes,
I think that's assumption 1. What you call this extra contextuality. So.
Extra contextuality is the fact that I attribute the same projector to all modalities, whereas there are different modalities.
That's correct. And that's sufficient for computing the next probabilities, so to say.
Yeah, well, and so
that's the same one. There are no hidden variables behind that. So
no, there are no hidden variable, but the psi does not give you the modality, so the psi is incomplete, which is a rude way to tell it. And so people always tell me, you are just repeating Bohr. So, you know, Bohr was telling psi is complete. And I said, no, psi is incomplete, sorry. But it's not incomplete in the way people thought it was incomplete. It's incomplete from the bottom and from the top and not from the bottom.
But then I have a very naive, simple question. So since the modernist argument is made so that you only need to drop one, and once you drop one, the problem is solved.
No. I completely disagree on that. This kind of stuff is what it was. There was a guy, I forgot his name, in London, in this conference where I was with Carlo and Alexia. There is a very big danger, which is what is called forced choice fallacies. You have very often forced choice fallacies Caribda and Scylla, you know, you have to choose between peste and cholera, ou bien Caribda et Scylla.
I agree. If it were a false choice, then I would agree with you. But sometimes they're not false, and so we have to understand whether the modern one is false.
It's forced. You are forced to choose between two things or several things, and actually there are other ones, but these other ones are ignored. And so, for instance, pest and cholera. What do you prefer between pest and cholera? I prefer none of them.
I mean, it might be that it's an instance of that. I'm saying that it might also be that it's not. So, but what I'm saying is, so suppose it is, like, grant me that it is. Then one day we're gonna check whether it's one or not. But suppose it is. Then if it is, then you don't need to drop 2 as well, because once you drop the assumption 1, you don't get to measure.
I do, because obviously, clearly, among the 3 you told, typically we drop 2. In CSM we drop 2. I added with this new idea of extra contextuality. We also drop 1 actually, which is more unusual. But we keep 3 because measurement have definite results.
And may I ask very quickly? May I ask you whether the drop 1, the fact that you drop 1 and the fact that you drop 2 are logically connected, or can you do either of them without doing the other?
What is 2? I forgot what
it's
is
dropping assumption 1 and dropping assumption 2, right? You drop both, right?
No, can you repeat what is 2? Because I forgot.
Oh, that the wave function always evolves linearly.
Yes. It's unitarily, you mean?
Yeah.
Mm.
Yes, we drop universal unitarity, which is already done. It's done in standard CSM. And with this new, algebraic stuff, we also drop 1 because we complete the psi, the usual psi. If you stay in type 1, you don't need to complete psi because, the observable is outside of psi. You say psi is an eigenset of the observable. So, and you learn in textbook, Cohen-Tanucci, where, the quantum set of the system is a vector in a Hilbert space. But I say it's not the quantum set of the system, or it's very subtle, actually. It's a class of modalities that we call usually the quantum set of the system. An equivalence class of modalities. But it's very, very close to my Cohen-Specker stuff with nice drawing and nice colors. So do you allow me to show you that?
No, let's go into the discussion, I think. Let's continue the discussion. Let's not go into the presentation.
So if, maybe, Caro, do you have a follow-up? I had one, but we don't have much time.
No, I don't want to monopolize the thing. So if you have there are more things, comment, but let's postpone it.
We have one more question, and then we'll see whether we can go back to that. Because I also had another follow-up.
Just a little thing to be clear on this Maudelin's trilemma. In your case, Carlo, the crucial point you reject is the third one, and then the second one is the consequence in a way. Is that would you agree with this?
No, no. I think that yes and no. No, you're right. I would replace the third one, but that's a key point. There are definite outcomes, but there are relative outcomes. That in that sense, I don't know if you call it a rejection. It's a rejection of course, if you take it as formulated by
the qualification.
Yes, it's a rejection. It's a rewriting of it. But also then the second is also rewritten. Because again, linearity, it's true, but it does not refer to the relative facts. You know what I'm saying?
Yeah.
Isn't it the case that the fact that you drop 2, well, you specify 2 in a different way makes you specify 3 in a different way? It's not the other way around. As I see it, is that once you make democratic the collapse process, as you say, then you redefine 2, you drop 2, and that, sorry, you don't drop 2 when it's redefined, and then that's reason to redefine 3. It's not that once you redefine 3, you have reason to go back to 2 and redefine the collapse. as I see it, is that once you make the collapse democratic, then you have reason to look at relative state, the relative facts.
Yeah, but measurement results are facts, and we just said that facts in Carlo's views are all relational and this is 3. So you requalify 3, and as a consequence, you have to requalify 2. But that's no.
Yeah,
you can play both way around. The result is the same. But I think about this trilemma, how you call it, this choice between the 3. Somehow there are a lot of discussion going on, and maybe let me tell you my view of CSM with respect to that, because Alexia has been saying there is CSM 1 and CSM 2. I would say that CSM 1, CSM 2, and CSM 3 in the following sense. There's one problem which is a measurement problem in a strict sense, which can be formulated, for instance, as you have to drop one of these 3, or there's a tension between 2 postulates. There's one problem is what is the ontology of quantum mechanics, how we want to think about that. They're not exactly the same thing. So it seems to me that CSM1 does 2 things different. One, it gives us a very nice language for the ontology of quantum mechanics. But with respect to the measurement problem, the solution is a textbook solution. It's a classical world, and with interaction with the classical world, there is a fact. That's what we learn when I learned quantum mechanics. I didn't learn there is a wave function. I learned there are postulates, and when you make a measurement, there's a fact coming out. And when does the measurement happen? When the quantum system interact with the classical world. So it's a standard solution. So that seems to me that CSM, that's not the interesting part of CSM. The interesting part of CSM is that it enriches the standard solution with a clean ontology from a nice set of initial ontological step, from which remarkably the formulas can be derived. And then there is a third question, independent of that, which is, all right, so what is this classical world? And this is what is addressed, it seems to me incompletely for the moment, but I think Philippe would agree, but by CSM2, by the idea that perhaps there's an infinite number of degrees of freedom, and there is a mathematics that can give shape to it.
Yeah.
Would you agree, Alexia?
Absolutely.
Okay.
That's fine with me also.
We have 2 or 3 minutes. We can discuss. Well, we can go 4 or 5 minutes over if needed. But do you want Alexia to? There was a question. Well, a topic you wanted to discuss. So we want to.
Yeah. Well, it's about my little obsession about randomness. So I asked the question to Carlo about how randomness was emerging in the framework of relational quantum mechanics, and with the voice, it's always better than with the mail. So, but just in the answer that you gave just before joining the Zoom session, Carlo, randomness is not related to some finite amount of information or finite amount of, or some discreteness in the equivalent of modalities. It's a disagreement between the question asked by the system to the friend and by the friend to the system in the answer that you give. So there is no quantization in the game in there. There is no discreteness. You see my point? Or, I mean, it's already 2 hours we are discussing. Maybe it would deserve a better conversation than being squeezed in the end of the session. But I'm just dropping this here. What I like with CSM is that there is this quantization that in some sense gives rise to randomness. And I don't see this in the answer that you brought.
I didn't answer to that question. What happened in my old 90 paper is that I gave a general discussion, but then I said, okay, let's forget the general discussion and start from scratch. So how can I think about it? Somehow it's a a pre-version of what you did later. I mean, just forget the formalism. And in fact, can I go back to the formalism? And then the way I thought about it is the following. Let me try to use a language close to yours. I have a system here. The system by itself has no properties. So I don't want to say the system has properties as a state, anything like that. It is in a context which, in the language I use, which is not exactly yours, there are differences, but it's similar. A system has a property because it interacts with something. So in that sense, it's like it in a context. You would say it's a context like your virtual change of context, because it's not yet classical. But it's a because it interacts in something. The interactions that it can have chooses a basis, in a sense. It chooses a set of modalities. And the language I used is that one system asks a question to the other, specific questions. Okay. And here are my first postulate, which is exactly analog, I believe, to your first postulate. Namely, I said the possible number of answer to this question is finite, which is the number of modalities is finite. Once you have the context, you have a finite number of modalities, okay? The second postulate I had, well, you can ask different questions, namely now you change context.
So changing the interaction between system and friend.
That's right. The same system, but now is interaction with somebody else, okay? Who's asking a different kind of questions. So in your language, this is a different context. And my second postulate is, in spite of the discreteness of previously, now there is something new that can always come out. So the previous discreteness is not sufficient to determine the outcome of the following. So now I've heard you saying that. I also want to say there are more questions than answers. So I can ask other questions which are not blocked by the previous, but are new. And since once I have the new set of questions, I still have the finite number of modalities, because in my language, this is the maximum amount of information that you can have. There's no more. Then the only possible relation between the previous one is probabilistic. Namely, once you know the new ones, you lost information about the previous one. The previous one don't mean anything. So the system itself doesn't have the previous property anymore. So the two postulates together give, now, and then the way I organize that is very good. So now we have a matrix, an n by n matrix, and it's exactly your n by n matrix. And I noticed that this n by n matrix could be, the entries could be the square of a unitary matrix, but I wanted something that selected this to be, and I couldn't. And you say, well, in a sense, if you take your construction and your extra contextuality, you can show that with some assumption this works. So it's the same logic, I think, with some differences. And the key difference is what we've been saying all over again. I mean, for you, this individual things that you change, you want to think about complete contexts, classical contexts. I was just thinking of different interaction one after the other one.
Okay.
Which I think we agree on all the physics, we agree on the mathematics, we agree on the basic concepts. The only thing is that, well, on the basis of that, do we want to take a classical world of given or try to reconstruct from infinite and do the ontology out of that? Or can we try to do an ontology before going to the step of the...
Yeah.
So I think we could stop here, but I'm gonna send you an email in the next days, and I'm gonna give you some possibilities about topics to discuss. Of course, there are already some ideas, and since that's a democratic process like quantum interactions, so I'm gonna ask you and you're gonna tell me what you prefer to discuss. And there is the recording, so I'm gonna share it with you very soon. And that's it, I guess. So have a nice
thank everybody. Also, thank you for the discussion, because I've been talking about relational quantum mechanics, but I'm presenting relational quantum mechanics differently after this discussion. I mean, this note that I wrote came out from this discussion. So for me, it was infinitely a learning process there. So very happy.
Definitely same for us, and thank you for this.
Yes.
Well, hopefully see you soon, and have a nice weekend.
You too. Bye.
Thank you.
Ciao, ciao.
Bye, Alexia.
Bye.
Bye, everybody.
Ciao.